involving the latest and greatest approaches of language models and model alignment strategies like RLHF and preference optimization and their variants. So I thought I'll motivate the talk with one of a part of the presentation that was shown at SC last year, highlighting the workflow we have and what implications are there in terms of the HPC needs, algorithmic innovations, etc. So please interrupt me anytime for questions. So I'll begin with a bit of the emphasis on the workflow, and then I'll go on to talk about the specific algorithms and the alignment methods, the results that we have, and then I can walk you through the Google Colab in the end if we have time. Right, so language models, I think, have become sort of the front end these days for a lot of the protein design and generation tasks, primarily because I think they make it extremely easy to generate mutations that are otherwise harder for even conventional methods like directed evolution or ML-assisted directed evolution and their variants to do. And yesterday, I just went through our model suite in terms of the genome scale language models. So the approaches that I will be describing here today is not constrained to only work with the genome scale language models. It can be any language model or any protein language model of interest. It can be ProGen, it can be ProGPT, and their variants and so on. But we have we developed the GenSlim model, so that's our sort of go-to when we do our experiments. The next point of highlight is so when you actually want to talk about like experimentally assisted and meaningful design candidates, a lot of validation needs to be done before even you send it to the lab. And that's where our integrated workflow comes into the picture. And that's basically a suite of scoring blocks that can be compute efficient or compute intensive, depending on the type of scoring you choose. We have a range, all the way from folding the proteins to performing compute intensive molecular dynamic simulations and reaction profile calculations. And once the workflow completes its cycles, and then it gives us the candidates, and that's what we assign sort of higher confidence before they're given to experimentalists or sent to the lab for further validation. So I'll talk about the details of our workflow, touch upon the scientific performance, and then I will talk more about the closing the loop with feedback approaches. All right, I'll skip this slide since I covered this yesterday, and this one too. All right, so where did this all start in terms of thinking about a feedback with a closed loop for design? Is our push at the laboratory level for an automated way of coming up with novel protein and protein sequences for different families, and to be able to have an automated way to integrate the fabrication protocols at the self-driving lab level, and to minimize the human involvement as much as possible. I think that's the overall goal, so that we are reducing the errors that would otherwise could sort of compound and proliferate. And more importantly, I think we can get much faster throughput if we have a closed loop system that's completely assisted with the design and fabrication protocols. So, how does it look roughly is what I have on this slide. So for this particular protein design application, so we would start with a large language model that's trained on a number of protein or gene families. Like I mentioned, it can be any language model, such as Progen, GenSlims, ProGPT, ProT5, etc. And then you query the model for novel sequences, and the generated sequences are then passed through a number of scoring blocks. And here it's up to the creativity and um, sort of the extent to which the validation needs to be done um, is what will constitute the number and the extent of the scoring mechanisms at this level. And once the filters exercise their measures, the filtered sequences are now what we would say as our highest performing candidates. And then they are sent to an experimental setup. In our case, it would be the self-driving lab. And the feedback from the lab is then taken back and used to align or refine the language models further so that every subsequent iteration, your generated batch is getting closer and closer to the design objective that the user specifies. And it's at the feedback level that we employ RL and preference optimization approaches, which I'll talk about. Okay, so details of the workflow. So a cartoon or a schematic of what we have is captured in this picture. So at the topmost level, I have labeled it as a training block. That's basically the language model that's instantiated, and it's getting trained after every set of the feedback comes through it, right? And then the next block is generation from that instance of the language model. And once the generated sequences are received, then there is scoring mechanisms. Like I said, we have sort of different levels of compute intensive scoring. The first level is a simple folding of the generated sequences. So what you want to ensure is that the sequences that are generated are not hallucinated in an extreme sense. So they should still fall within some sort of natural prescription and constraints of the folds that are seen in nature. So you do want to make sure that the generated sequences are folding and are having reasonably good folds, which is given by the folding measure of the module you choose. In our case, we have folding modules ranging from alpha fold, open fold, ESM fold, and so on. For practical reasons and for scalability, our choice is ESM fold because it's more end-to-end and it's much faster compared to alpha fold to produce the final folded structures. So at scale, what we see, like if we do a full scale run of this work on Polaris, we can fold at the rate of about 100,000 sequences per hour, right? So that's if you have all the resources. And so all the sequences that are generated, like I said, are folded and their folding measures are logged. And of them, the top P%, and that's a number that is up to the user to assign, is what is then sent for further filtering or scoring by the next level of scoring mechanism, which in our case, it's just dynamic molecular dynamic, a dynamic stability measurement using AMD simulations. And by that, I mean that the folder structures are taken as a starting point, and they're all set up to go through straightforward OpenMM AMD simulations. And they run for a certain number of time steps to make sure that they are at that in that MD setting, they are structurally stable for a certain minimum number of steps. Because what we have seen is, even though some folds are found to be good enough, that is, they would satisfy the folding measure, but sometimes when you simulate them, the protein will just unfold and will become unstable. So to sort of avoid or capture and filter out those corner cases, it was important to incorporate the stability block with molecular dynamic simulations. And since it's much more compute intensive than just a simple ESM fold, of course, the rate goes down. It's on the order of about 1,000 per hour if you have the full machine resources. And
Gautam,
yes,
couple questions here
sure.
as you jump there. So when you run the MD calculations, do you run in? Is there a workflow that is automated? What is this, or you're going to run through each of the blocks in detail?
So this entire workflow is automated, Venkat. I'm not sure. I think.
So then, so then couple questions on that, or will you go through each of these blocks in detail, or can we ask questions on the blocks now?
You can ask questions. I don't think I have slides going in too much detail.
Perfect.
Because,
so then we can. Okay. So then I can ask a couple questions here. So the MD trajectories, the automated workflow, so it automatically generates and then does a bunch of I guess there's some NB, the NBT and then maybe NPT, all that stabilization runs. Is there some automatic error handling and stuff like that, or how do you sort of ensure that the trajectories generated don't run into some issues and so on?
So we have an automatic error handling in the sense of we just capture them and then we discard them. Like if the so I think I have a plot that shows that if the RMSF value, for example, from the trajectories is going above a certain threshold, then those trajectories are discarded automatically.
Got it. Okay. So let me just make sure I capture this full thing. I mean, I think I still haven't gotten to, you haven't presented activity, but so the generation part, right, is just sequences, right? So that's pure text, right? And then then for the next one is done with open fold. Is that what you said?
So we in the workflow, it is ESM fold because that's much
ESM fold.
faster.
Okay, yeah, ESM fold. And so that takes that now is a 3D geometry, correct?
Correct.
Okay, and then the 3D geometry is then given to an MD simulation, and so the 3D geometry now is I guess 4D now, right? Because 3D plus time, right?
Correct.
Okay, great. Thanks.
Yes.
Yeah, look forward to activity next.
Yes, I think that's the most interesting one. So so once the MD scoring is done, and as Venkat rightfully clarified, it's only those trajectories that are having sort of bounded root mean square fluctuations in the positions, for instance, are the ones that are kept. The rest are discarded, and from the ones that are kept, the user can further filter the top, say, Q% for sending down the final evaluation block or the functional evaluation block, which is computing the activity of the structure. In this case, I'll be showing the results for a certain enzyme called malate dehydrogenase. So we are just doing the surface reactivity for that. And the reason you want to further select or downsize the candidate pool for this block is this gets much more computationally intensive. And that is because, let me see, sorry. Yeah, I think probably this captures that, or okay. So roughly what I wanted to say was, for the reason you see a much decrease in the rate here is because for each candidate that you select from the MD trajectories, a EVB computation involves 50 different MD simulations. So if you choose 100 candidates, then it quickly becomes 5,000 simulations. And each simulation is assigned to a GPU, and they need to be run for at least 1 hour. So here, the batch size becomes critical from the training point of view. So if you increase the batch size, your candidates for functional evaluation, quickly scale up, and that becomes very computation intensive. So before you look into the resource utilization, I just want to give this result plot. So with this workflow, what we achieved was, for this particular family of malate dehydrogenase, we were able to identify um, novel candidates that had this reaction profile that was much more favorable than a natural MDH sequence. So let me go into the plot a bit more. So what you're seeing is the reaction coordinates on the x-axis, and then this um, uh, a quantity that captures this reactivity we call PMF on the y-axis, and you're seeing the reaction profile. So basically, each curve is coming from is constituted by 50 different simulations. There are 50 points on each curve. So the dashed blue curve is what you see for the natural MDH, just denoted as 5-MDH. And then all other curves come from novel generated sequences. And of them, you see that a number of those have a barrier height lower on average by, the best candidate has a barrier height lowered by about 4 kilojoules per mole. And interestingly, the reactant side is also more stable than the natural counterparts by about 4.89 kilojoules per mole from the best sequence candidate. And so that was very interesting for us to see. What was more interesting was what is like, where do these sequences sort of lie in a semantic space of the language model, right? So for those who attended yesterday, I went into this idea of projecting the embeddings from the language model after it gets trained. So that's sort of what you're seeing on the plot on the left. So there's like 4 layers to this plot. So I'll try to unpack that. So this is a 2D projection of a much higher dimensional space, right? So there's a lot of compression happening here, but still there is some level of interpretability. So on the lowest layer, you have this gray plot, the grayscale plot, which are the natural MDH sequences that went into fine-tuning the starting seed model. And they are color-coded by the GC content, starting from the low value to a high value. So that goes from left to right, sort of in this direction. And then at the next level, what you're seeing is the generated sequences. And they're all the generated sequences are color coded by their fold measures. And that's what you're seeing as these tiny dots. So starting from, so also from sort of right to left, you go from small GC to large GC. And every dot that you see here on top of a gray region is a generated sequence, and all of them have a good folding measure of a value greater than 0.8 in terms of what is called as a PLDTT score. That is part of the ESM folding routine. Okay, and from those candidates, the starred ones are the ones that were further filtered, and they were subject to the structural validation or the dynamic structural validation by MD. So you see lesser stars, right, compared to the finer dots. And from further down selecting from those is sort of the a really small island here, which is sort of the tip of the cone, where we got these top 12 candidates that were computed for their reaction profile. And one of them was found to have an activity, for about 4 kilojoules per mole less than the natural. But I think interesting thing is, not only were they like functionally better than the natural variant, but also in terms of the latent space projections, they are out of distribution compared to the gray dots below them, right? Because then these regions are not overlapping with any of the natural counterparts that were used in the training data. So that was the another, I think, interesting observation from running that workflow. Sorry, there was a lot to unpack there. If there are any questions, I'm happy to pause here.
Yeah, this is great. Yeah, this is exactly the kind of thing that I was hoping we would cover in this session. Anything you can share on the accuracy level of the EBB for these kinds of activity assessments? Can you think? Can we, if we wanted to sort of build a multi-fidelity style, is there something that we might think about there?
That's a great question, Ankit. So I think so. One process that we have started is we can correlate some of these reaction profile values to experimental measurements, and I think that would be the sort of the best validation that we can get. And but the problem is also that we only have about 96 candidates that have been experimentally measured. So it's not a large enough sample size for that, validation either. So I'm not sure if that answered your question, but that's what I think is ongoing with the experimentals now.
Yeah. Okay. Great. No, experiments is one, but there may be other higher fidelity calculations you could run that are maybe lower throughput than your empirical valence bond. So that's I'm thinking along that direction.
Okay. Yeah. Yes. So we have a couple of collaborators in Caltech. So the idea is to use more quantum-based simulations like OrbNet-like approaches that would have much higher fidelity than what the EBB within the AA, OpenMM, and AMBER context is doing. So that's, I think, one.
Yep. So
One idea that
this is from
pursuing,
Tom Miller's group, the OrbNet team.
This is from Francis group, Francis and Anima.
Okay. But the OrbNet.
The OrbNet, I think, that's whom you're
that's from
referring to.
Tom
But
Miller, right?
the people, yes, yeah. But I think the people who are trying to do this for these systems are working with Francis and Anima. So.
Okay. All right. Great. Yeah. Thanks.
Thank you. All right. So I think it will be interesting to go through some of the numbers in terms of the performance of the application, at the level of utilization of the resources and the throughput. Sort of gives you an idea of the balance you need to strike when you allot resources, and as opposed to the amount of science you can get out of it. So, for example, for a 64 node run on Polaris, so you're able to achieve a sustained sequence generation rate of about 100,000 per hour, and all the generated sequences are folded. So the folding rate is about the same as the generation rate, and the simulation rate is about 100 per hour. And here I have just given the exact numbers of the number of nodes that were allotted for the generation, the number of nodes that were used for folding, the corresponding batch sizes, and what is the ratio roughly you get for the number of reaction profiles that you can get for every n number of RMSF or straightforward MD runs. So I think, so if you just think about the final output there, which is the reaction profiles, at the end of about 6-hour run on 32 nodes, you can get up to 12 reaction profiles. Of course, these are all numbers that can be tuned further, so the user can choose to allocate more resources for this and less for the earlier steps, and so on and so forth. But this is just one setting, and I just want to share the numbers for that. All right. Also, so here I just want to show that.
Alex has a
yeah.
question.
So in the previous thing,
Alex.
it looked like you were seeing kind of like steps in the generation.
Right.
And I'm assuming that the upper left hand, that's just batching, but in terms of the right plots,
hmm
why does that happen? And does it, like, does it matter, or is this just like a fixed
Oh,
thing?
so no. That's a really good question. So why this happens is because it's roughly at the end of about 1.5 hours is when you are like sort of completing the folding of all the generated sequences, and then dynamically the resources are now being allotted for the RMS of computation, and that's why you see that sudden spike here. And after this, so once some candidates are completed at this level, they are sent to the EVB calculation. So it's sort of, you can think about it as like roughly not, things are not exactly serialized, but as and when things get completed for the next block, the workflow dynamically manages that. And so this is just a consequence of that sort of orchestration. Did that answer question?
Yeah,
Alex?
that did. Thank you.
Yes, thank you. All right, so here I just want to show, I think, highlight a couple of things. So what you see is GPU utilization, node utilization, and a plot that we just discussed when Blanket asked about, how good or bad are the sequences when they are simulated by MD. So the GPU utilization for our workflow is really good. It's roughly a profile like this. So once again, I think depending on the particular application, the user can go and tweak the config and get the optimum numbers that they want. This is just for this one particular run. And in terms of making sure that the generated sequences are not like completely, sort of garbage, and they unfold during the, simulations, the workflow keeps a tab on the root mean square fluctuations. And this is roughly a scatter plot of those, the mean of the root mean square fluctuations as the workflow is progressing, right? So you can see here that in our case, I think if I remember right, for values greater than 2.7, for example, the workflow would treat them as not acceptable and they would just be discarded. It's only the candidates below that threshold that are kept in the queue for further down selection in the EV block. But at least from what I've seen, I think this sort of maintains a bound. I've not seen values go too crazy either. So that's sort of a scoring point, I think, to the fine-tuned model to start with. But this could change for the model depending on how it was fine-tuned and so on. All right. And this one is one of the runs we did at full machine scale. So this was across all of Polaris, and it was run for a total of 6 hours. I think if I remember right, we generated and folded close to 1 million sequences. So that was quite a feat. But there are more details to that I was not going to. I just wanted to give you a sense of how it looks for workflows run at full machine scale. All right. So if there are no questions, I will move to the more algorithmic side of how we are taking the feedback back to the language model and the different approaches that we have employed.
Yeah, this is fantastic.
Thank
So
you.
yeah, can you go back to the previous slide?
Sure.
So these kinds of the right plot is very, very nice. That kind of is that visualization also like automatically generated while that is happening? Like, can you see?
Uh, so we we don't yet have a GUI necessarily, but we can, like, because the log files are there, and we can visualize in real time if we want to. But this is a post visualization.
Post processing thing.
Yeah.
And then couple of questions on the sort of HPC side. Right. So when you're deciding these runs and node sizes and so on for these various things, is there a sort of a calibration loop in that where you sort of test whether that is sufficient or not, or you do it out of the loop, in that you sort of do that test before and then lock in the node sizes and all that, and then run that at fixed node size independent of the exact system that you're evaluating at any given point in the loop?
Right, yeah. That's an excellent question. So these runs, they were all like sort of calibrated a priori. So, but yeah, so it'll be great, and something that we're thinking about also is if you can automate the calibration.
Yeah,
also,
exactly, right.
So,
I think it would be,
yes.
I think this would be very, very interesting, and maybe we can, tease out some of these things in the computational science agents hackathon, right? Because you can imagine that, the static node run case, right, may not be, I mean, I guess it might be okay in general, sort of for the average case, but there may be some benefits to be had, right, in terms of being able to sort of do that resource allocation slightly more efficiently for each job, right? So you might be able to reduce the number of nodes or increase the number of nodes, and things of that kind, especially if we can, I think we sort of mainly focus usually on the sort of technical metrics, right? Like in this case, evaluating activity or like other kinds of stability. But there's probably another axis around sort of computational, time, resources, that axis, right? I think that if we can bring into the loop, I think it would be very, very exciting, because the throughput, per hour, right, is sort of has an implicit assumption around sort of how much resources, right, you are giving for that particular task. And so I think some, efficiency there, right, would be good.
Correct. Yeah. No, totally. Yeah, completely. So, yeah, I'm definitely all for that, right? So we have been thinking about that too, because quite a bit of time is actually spent in all those a priori calibrations. If there's a way to automate that more efficiently, then I think that would be the way to go. So, awesome. Yeah, we're happy to definitely chat more during the hackathon.
Yep.
So,
great. Any
awesome.
more questions?
Just a quick follow up on these profile plots that you have. Is this, what are you just like logging like from NVIDIA SMI? What's the utilization, or is this where, like, how are you getting these from the logs?
So we have like more than just NVIDIA SMI logging, but at least from the GPU utilization standpoint, that seems good enough.
Okay.
Yeah. But you're right that it's possible that the GPU is just occupied and it's not doing anything, and we don't want to log that as our utilization. So yeah, there are more involved performance metrics that are also available. But if a user just wants to do NVIDIA SMI, I think that's fine for the most part.
Could you give an example of one of those performance benchmarks?
For example, so there's a suite. I don't know if it's exactly open source, but it's called, one of them is called MLPerf.
Okay.
It's Venkat in Argonne is one who sort of heads that. So that can go at the kernel level and actually do the more bare metal measurement.
Yeah. Okay. Like an NSYS type, NSYS profiling type thing. Okay.
Right. Yeah.
Gotcha. Thank you.
Yeah. Awesome. All right. So then we can proceed to closing the loop with the feedback. Here's where I think the interesting algorithms come into play. So the work was inspired by what developments happened in the natural language world. So one of the earliest of the feedback approaches is, I think, formally, then I don't think anybody called it that, but it eventually got its name as reinforcement learning from human feedback. Uh, so this was sort of popularized by this paper by OpenAI in 2023. And eventually we all got to find out that that's the algorithm that went into making ChatGPT work as well as it does. So this is just a sort of quick summarization of what they talk about in the paper. I just want to give a sense of abstractly what this algorithm is and why it is of interest to us. So first of all, we are using more LLM-based approaches for our protein design, right? So then naturally, we would like to have a feedback approach that aligns with that setting. And so hence RLHF, and more recently, we have preference optimization approaches that seem to perform better than RLHF in some cases. So what is RLHF, right? In the context of language models, if you can think about the language model as a policy of its own, so policy is a term that people use in the reinforcement learning community. But if you think about the language model itself as a policy, then what is the mechanism in which you can take some feedback from a human user or the AI model to further refine the weights of your policy or the language model, so that in every subsequent output, you're getting results or generation that aligns more carefully with what the user or the human wants. So the way the recipe that they prescribed, right, in this paper is first you collect whatever data you need, and then you take a pre-trained model, and then you do the supervised fine-tuning of that pre-trained model with your specific domain data of interest, right? So it could just be pre-trained model, could have seen all of internet, for example, and your specific domain data could just be a bunch of weather reports or financial reports or something along those lines. So once you do this supervised fine-tuning, also known as SFT step, that sort of becomes your starting seed model for the RLHF feedback. And the feedback comes through a different model, which is the reward model in this case, which is what they describe here in step 2. That's nothing but a model that could be a simple classifier, or it could be a simple regressor model, but it's still a model that needs to be trained. So you need the data for that. So once you have adequate label data to do that sort of training, then you can sort of arrive at a reward model that you think is reasonably good enough that can be used for the feedback, right? And then the third step is you're putting these two together basically, and that's what is captured in your loss function that that they talk about in the paper. So this is just one formula from there. Basically, in the last step, this is the function that's providing the gradients to go further and refine your seed model to align it as best as you can, right? And it has different parts. This r theta x comma y is nothing but your reward model. The pi RL is the model that's being trained in the RLHF setting. The pi SFT is your model that comes from step 1. And then they have an additional term, a weighted term, that is just simply doing a tuning of the instance of the RL model itself, right? So you'll see different implementations. Not all of them necessarily have this last term, I think most of them just stick to this component of the loss. But in their paper, they discuss that having this extra term, which they call as PP or PTX, is providing some additional benefits at scale, for example. Okay, so that's all I want to talk about RL-HF approach. How did we use it in our application? So that is just captured by the schematic. So like I said, you have a seed model, which is your pre-trained model. In our case, it's the fine-tuned model. So it would be a model fine-tuned on the MDH family of sequences. And then I talked about the scoring blocks, right? So once the generated sequences are subject to the scoring blocks, then you can get the feedback either in terms of the reactivity profiles or feedback at the level of the MD simulations or feedback at the level of folding. You can choose which level of feedback you want. But for more interesting purposes, say we are taking the feedback from the catalytic activity, right? So that sort of becomes our reward model in this case, right? So you're just saying that sequences with catalytic activity better than the natural MDH variant is what is of interest to me. So you are rewarding them and you're penalizing the sequences with lower catalytic activity. And that's what is sort of, gives you this RL loss, which I described in the previous slide. And you do the backprop. And the one thing to be noted is you have sort of two instances of the model here, right? So you have the model being fine-tuned and you have the reference model. So that adds to the compute at the training level. So I think that's pretty much how we incorporate feedback and how we employ the RLHF mechanism for this particular protein design application. So quickly, some simple but still cool results that you can get is it doesn't have to be a single objective, like I mentioned. You can use a combination of the different feedbacks from the different scoring blocks. So what we have shown is for the MDH case, we can use sequence diversity as a feedback and improve on that, and or choose the sequence length as a feedback and improve on that. And another illustration that I just want to show is like you can do this for any family. Doesn't have to be MDH. So here you see that if you just simply wanted to enhance the population of a subfamily within a protein family that is otherwise not available in the training data or in the bioinformatics database, you can do that too. Like this is a family of lysozymes. So these are all experimental or naturally available lysozyme sequences, but each color is a subfamily within the lysozyme family. And you can employ a classifier reward model that can skew your RLHF mechanism to fine-tune your model and result in a final model that is able to preferentially generate one of the families compared to the others. And that's basically what is captured in this plot. So before RL, this is sort of the ratio of the generation for the different families. So sorry, before just the ground truth data is the black bars. The baseline generation from the SFT model is your red bars. And after RL, since we wanted to prioritize this particular family, you have much more generation of that family compared to the other. So it's just an illustration with RL. But of course that, we have a much cooler result in terms of taking the feedback from the catalytic function, and we are able to generate MDH sequences that are average, lower barrier height, better reactant stability than the earlier iteration of the EVB output. So that was also part of our results that went into the Gautham Bell submission. Like I can share that plot, but I don't have this on the slide deck. All right. Is there any question there, or can I move to,
Yeah, this is really impressive, Gautham. It's a very, very nice work.
Oh, thank you. Thank you, Adrian. Yeah.
Just kind of one
Yes.
question.
Sure.
So I believe you're doing a decoder type architecture.
Correct.
I'm curious training like in an encoder only architecture, like, oh, this would be cool, but I think I'm kind of not able to do this. Which that is correct. Like, is this, or can RHFL be applied to kind of like bootstrapped onto something that's not necessarily trained for sequence generation?
So that's a good question. So the particular way in which RLHF is formulated, I think it sort of ties well with more like decoder or encoder decoder approaches, right? But I don't see any limitation in generalizing that approach to something that is not just encoder decoder or decoder architectures, right? Because as long as you're able to generate the logits and get the log probabilities from the logits, you can still have this layer on top of that. Does it answer your question, Alex?
Yeah. Thank you. And then I guess the other question, so it seems like most of the like criteria and the objective that's there are fine tuning is going after is property based, like things that can be predicted and like measured.
Mhm.
Whereas like in say like a Dota match, or like a lot of the tasks that are traditionally like the NOIP are being used for, it's like you don't really know what the property is. You just know what you want, right? Like if you won, you don't necessarily know why. Do you see like this especially in like the biospace moving in that direction? Like want to build, we don't necessarily want to say that the drug has this property or the compound has this property, but just whatever it is that gets us the thing that we like? Or is that just like way harder to do? I think it's way harder to do. It's
So not sure I'm following your question, but is it that we're not necessarily having a very defined objective, but something that's more loose in that sense? I'm sorry, I don't.
yeah,
If you could repeat that,
yeah. Just to say it again. So again, in the electrolyte space, you'll often hear about people want to like design a molecule that would maximize your conductivity because that would let you do fast charging.
Okay.
But then the flip side there is that tends to be built around this idea that we're going to say some kind of a filter window, like I need a conductivity of at least this, I need my density to be this, and anything else isn't going to work. But I think it's DMC up until the point of that discovery, if you had used the filters that were being used at the time, you never would have found DMC, and then we never have lithium batteries, and people would be sad.
Okay, I see what you're
Right.
asking. Okay.
Yeah,
Yes,
I think that goes to sort of the challenge of filter-based approaches, right? Because in that case, right, what ended up happening is you could use a mixture, right, and then EC, which is a solid, right, would not have been picked up with sort of standard filters, right? And I think that gets to sort of yeah, like how do you assess? It's actually a very interesting question of how can a human actually provide feedback on these like very I think it's not so easy to provide feedback
right.
in this sort of style, because we actually don't know the reward. Like it's not so easy for me to say whether this electrolyte will have high conductivity or not, right? Because that's a very tough because property value, right, is a very tough thing to get feedback from. And I think, this is actually, I think, getting to the heart of sort of these kinds of questions around how do you incorporate sort of expert humans' intuition, right, in the feedback loop. And so I think it's a very exciting open area.
Yeah, totally. Yeah, I think yeah, it's quite open ended, right? So it's much harder to fit in this context. So actually, that reminds me. So one
Yeah.
of the questions I think For example, our collaborator at Caltech, Nobel laureate Francis asked was, can we use all of these fancy tools to come up with novel folds that we are not seen in nature? And that's a very open-ended question, and there's no straightforward answer to that. So
yeah, so
um,
actually, I think this is the angle that would be very, very interesting for us to maybe even pursue in the hackathon. Is
mhm,
the and Love Varshney and the Tuesday session gave a very nice talk about computational creativity, right?
okay,
I think and it turns out that you can sort of show that it ends up being related to sort of the KL divergence between sort of
I see.
the two distributions, right? So and of course the interesting, so if you think about I think the question that sort of Francis is implicitly asking, right, is show me something that would surprise me, right? And I think
Correct. Exactly.
and
Yeah.
I
Yeah.
think this is really, and Karthik also has been sort of forcing us sort of to try and think about the scientific foundation model. What can it produce that would surprise an expert, right? And I think it's very
Correct.
clear that today these models are very good at saying whether a candidate is good or not. Also, probably good at generating candidates that look good, and an expert would say, yeah, that makes sense. That's a good candidate that you picked. But the next step, I think, is that surprise or curiosity element of
Hmm.
how could I sort of surprise an expert, right? And I think that's at the heart, and I think Alex is sort of getting to this point of when I sort of asked them to think about this problem, right? Like, how would you have one of these models, right, make a Nobel Prize winning discovery, right? Like,
Exactly.
and
Yeah.
Nobel
Yeah.
Prize winning discovery is not usually around just optimization, right? It's a
Hmm.
combination of optimization, understanding, and an element of surprise, right, and novelty. And
Right.
I think finding clever ways to incorporate those kinds of ideas, right, into the feedback loop, right,
Hmm. Hmm.
could be very interesting, right? Maybe the feedback loop is not so much on the reward itself, right, like the property itself, but maybe it's along these lines of, oh, would I have thought about that, right? And I think that could be a way to sort of solicit expert feedback, right? Because that's sort of a more actionable thing. Um, so I think it's a very, very exciting
No. Right.
direction.
Yeah. Oh, completely. Yeah. Totally, Venkat. So I mean, we also like you. You're exactly nailed the point, right? So these are all great, but can it do something that like a Nobel laureate would like? If something, for example, if we can come up with a fold that is possible but has not been seen in nature, and if that convinces Francis, then I think that's an approach that would be really breathtaking. Um, yeah, I like what you're telling in terms of um, sort of the exploratory aspect as not constrained by filter-based, property-based approaches, but more of I mean, I think you used the word ideas as opposed to measures, right? So
Just kind of a point of information that is correct in terms of how this is being framed currently. It's trying to generate things with a particular set of properties. Yes.
correct. Yeah,
Okay. Just thank you.
yeah. No, so I think um, I don't know if there's any other approach that or method that can do what Venkat was describing. We would truly be at the forefront of such a thing if we were to attempt it, right? So
Yeah, fantastic. Yeah, keep going.
awesome. Um, all right, so Venkat, I think with your note, I kind of feel dumb to go with the rest of the slides, but I think I will still talk about the other approaches that are there, which we could incorporate. Um, so
Yeah, go ahead.
in a vein similar to in a vein similar to RLHF, approaches, people came up with more variants, so to speak, um, that have shown to perform better than RLHF, right? So one of the earliest of its kind is direct preference optimization, or DPO. And this method is very cool because they formulated from sort of first principles a statistical approach in the context of the language models. And what they found out was there's a way to do this alignment without needing a reward model. And hence the title of the paper goes, language models are, secretly reward models. And basically what they showed was, if you can have a data set that adequately captures your preferences in terms of what you want and what you don't want, then your language model is able to sort of implicitly learn that via an implicit reward model. And I would really recommend anyone who's interested to go read the paper carefully, because they go through the derivation of how they came up with that idea and what was their intuition and why the method works. You can sort of very clearly understand that. But for this, just for this talk, I want to just touch upon what the loss function looks like and what the results they had in their paper. So why this method would be a preference, maybe compared to RL approaches for some cases. So the loss function looks simpler than for the RL case because you've gotten rid of the reward model, but you have more instances of the policy now, right? That's the trade-off. So if you can, what they show is one of the terms here can now be treated as your implicit reward model. And that's how they sort of bypass that requirement. So here, W refers to your preferred response, and L refers to your not preferred response. And pi is your language model, theta is the tradable parameters. Pi reference is your reference model. So that is the model you start with, you make a copy, and then the copy is what is getting fine-tuned. That's pi theta. So your pi reference is sort of not changing during the training process. It's just, as the name goes, it's just providing you a base or a denominator for telling you how much your current policy is being changed, compared to your reference policy. And you have the specific ratio, right? So you have the ratio of the model being trained to its reference model for your preferred sequences. And that is subtracted from the ratio of the same quantities, but for your not preferred sequences. And then these are all going into a sigmoid, a logarithm, and then you have a negative logarithm of that. So it's a simple loss function, I think, to implement. I think it's much more simpler to scale and do all of that with this particular loss function from an engineering point of view than a PPO or RL-based approach. I think for those reasons, it became very popular very quickly. And one of their plots in the paper is this. So they use a sentiment generation as one of their downstream tasks. And what they show is, the Kale divergence of the model being trained with respect to the reference model is, doing better with DPO compared to a PPO approach. That would be the RL-based approach. So these yellow dots are from the DPO approach, and reward is the pseudo reward that they define in the paper. And then, as you can see, for different PPO approaches or implementations, they're all still below the curve compared to the DPO curve. And then they also do it for the text summarization task, and of course DPO is doing better than PPO for those cases also for a wide range of sampling temperatures. And they do a more detailed validation showing why DPO seems to be working better than PPO for a number of benchmark tasks that people do in the NLP world. Okay, so that was sort of our draw to the method as well. So once we we're comfortable with the oil-based approach for our application, so it's more intuitive, much easier from an engineering standpoint to implement and scale, and you don't need a reward model. So I went ahead and
just a question, and maybe you're going to get to it. Have you looked at using like KTO as opposed to DTO, or just?
So I've looked at actually a number of variants. KTO is not something of choice for us at the moment for different reasons, and we can discuss that offline too. But DPO on variants is what, at least for this application, we are seeing like pretty good results.
Cool. Thank you.
Yeah. All right. So I went ahead and pursued two flavors of DPO. One is the more generic one that I just described, and then the other version is a tweak to the generic one, which I call as a self-aligned DPO. So quickly with the schematic. So for our task, if we start with the data set that has a labeled experimentally fit sequences and experimentally unfit sequences, so those two would what correspond to our preferred versus unpreferred samples, respectively. And like I explained with the loss, you have a model, you have a reference model, and then they provide the log probabilities, which are the components of the loss function. And then you compute the loss function, you do a backprop, the model gets aligned, and so on and so forth. In a self-aligned DPO, what is of interest is, say if you don't necessarily have a this bifurcated data set to start with, right? So if all you're given is a pretty good fine-tuned model on the family of sequence you're interested in, and if the assumption there is that the model has learned the has implicitly learned the fitness landscape for that family well enough, then are you able to sort of generate more preferred sequences compared to the unpreferred one in a self-aligned manner? So when I say self-aligned, I just mean that the model, the reference model, and the model generate the sequences, and then you have your reward structure. So in this case, you need a reward model. Sorry, you are bringing that back, but you need that to bifurcate the generated data set as preferred and unpreferred. And then you're putting that into the DPO loss formulation, and that is what is back propagating, and it's aligning the model in that manner. Hence I call it self-aligned. And this is of interest to us because it fits very well in the context of self-driving lab setup, right? So if you don't have an external oracle that is providing you external label sequences, but all you depend on is your only generative model, then this sort of approach you would want. So yeah, those are the two modes we have. Just want to quickly show like a typical training curve in the DPO setting looks like this. You have the rewards and the loss. These are the pseudo rewards, keep in mind. And then, so for a couple of families, I want to show what DPO does before and after, just like what we saw for the lysozyme case, right? So for example, for the yeast family, if you were to make a histogram of the fitness data on the sequences at the experimental level, so what you have is you have more unfit sequences to start with and less fit ones that were measured, and then using those in the DPO mode, you do the alignment, and then after DPO, you're able to preferentially steer the generation towards more fit sequences compared to the unfit ones. And all the validations were done to make sure the generated sequences, folded reasonably well, they had the right length, properties of this family, etc. But quickly, in terms of also the semantic meaning, what you can see is, so before DPO, the model's projection of the fit and unfit sequences looks like this. So the fit ones are green and the unfit ones are the maroon ones. And then post DPO, you can see that there is like a much greater enhancement to the generated sequences from the fit sequences compared to the unfit ones. And what's cool is there's sort of not an abrupt disconnect as the model aligns to go from one to the other. It sort of naturally mutates the unfit sequences to sort of generate this cloud of more fit sequences. That was also very cool to see for us. And similar results with many other families, but I'm just showing two for an illustration. And the only difference for this family was when we started, the experimental sequences were about 50-50 fit and unfit, and post DPO, there was a preferential generation of fit over the unfit. And similar evolution in terms of the semantic evidence when we look at the prediction plots. So I just want to quickly show you, like, if you like, we scaled it. So I did my own custom implementation of DPO on our methods, so that it was more intuitive for me to see how we can scale them and so on. So we were able to take that and scale it in the context of Megatron Deep Speed, which is what helped us cross the exaflop barrier in our orbital submission. So just want to show how some of the training curves look. They're not necessarily smooth, right? So that's what you would expect when you start scaling. But still, they follow the profile that they should, and the outputs look really good. So here I just want to show that a lot of times a question that would come to me is, great, these are all like working, but if you were to employ it in the context of a self-driving lab, what the experimentalists care about is this notion of sample efficiency, right? So they want to get to the desired objective at a not so slow rate, right? Because at every iteration, you're going to order a new set of samples, and it's going to be expensive and take time to procure. So this just shows that for one particular family that I think is MDH, the sample efficiency is pretty good in the sense that if you were to increase the batch size, so the dash curve was a batch size of 64, and then the solid curves are a batch size of 128. So as you double the batch size, the rate at which the model generated preferred to the unpreferred sequences as it got self-aligned improved. So that gives you an idea of the sample efficiency, and that's what this plot is showing. So it's just plotting the fraction of the preferred or the unpreferred generated as a self-alignment happens. All right, so I think this is not just to show that generated sequences folded well, and this is just sort of a controlled example that I wanted to, it's a good demo. I think that's what I would want to show in my collab too. Is so, for example, if you take the MDH family, and if you take a simple property of GC content, which is the fraction of the G's and C's in the sequence, one control experiment you can do or ask yourself is, if I started off with a fine-tuned model that saw sequences of only a certain range, am I able to do this alignment and result in a model that is able to fill the gaps that the seed model missed out, right? So that was sort of the idea here, and that's what is in the collab. So for the MDH family, at the ground truth data level, the GC content distribution looks like this. So that's the black curve. So roughly the values go from about 30 to 75 plus. So what I did was you take the sequences that are GC less than sort of 45 and greater than 60. And that formed my data set for supervised fine tuning. So I fine tuned a model that only saw those sequences, right? So there's no way that model, no matter how well you prompted it, would be able to generate sequences in this valley. And that's why you have a valley there. Then, if you are exposing now the model to sequences in the 40 to 60 range via the alignment mechanism, in the end, after reasonable convergence, your aligned model should then be able to start generating sequences that starts to fill the valley, right? So that was sort of the control experiment idea here. And a training curve for that in terms of the reward looks like that. So that's one thing I want to share. I'm sorry, I rushed through the last few slides. Were there any questions?
No, I think, yeah, good, keep going. Yeah.
Okay. So I think one of the more recent variants that of interest is there's so many variants that have been coming up just in the last few months. But one thing that is to be noted is I think this method of ORPO, which is nothing but odd. I think informally it's just odds ratio preference optimization. And what they have proposed is very cool too. Is they have improved upon DPO. It's still a DPO variant, I would say. The improvements are they have shown that you don't need to do an explicit supervised fine-tuning step, but a single training protocol can capture that and your alignment. And they also shown that you don't need to keep an instance of the reference model. So though theoretically nice, from computational standpoint, I think keeping an instance of the reference model starts to become a pain as the model size increases. Because if you think about it, all it does is provide you just with a reference. Its parameters are not changing. So if there's a way to, sort of do the alignment without the reference model, then that's welcome from scalability standpoint, right? But what they show is that the output, the generation is also doing better than DPO for the different models that they considered. I think they consider the Llama family, Zephyr and Mistral. And there is a, these are the alpaca eval results that they show. And they show that ORPO is doing, slightly better than DPO. But quickly, in terms of the formulation, the way they get rid of the reference model is they just replace the denominator with the concept of the odds. So instead of pi theta and pi reference is now replaced by 1 subtracted from pi theta, basically. So instead of reference model as a denominator, you have this odds-based concept that they have adopted. And otherwise, I think the rest of the formulation is very similar. And the way they get rid of the SFT step is they simply combine it into one protocol. So they have the SFT negative log likelihood component combined with the weighted odds ratio component, and that's their ORPO formulation. I have some initial results that are promising. So it's of great interest to us because from an engineering standpoint, this will make a huge difference as we scale to large model sizes. So I will leave it there and I just have the summary slide. Are there any questions, or I can quickly walk through the collab?
Yeah, let's go through the collab.
Okay. All right. So for the purpose of this demonstration, I'm making use of the TRL library from Hugging Face. But like I said, we have our own custom implementations that we have scaled. So all you need to do is, so I have access to A100 that sort of makes the training much faster. So I'm going to try and see if I can connect to that. Okay, I have that available. So let's just get those libraries installed. Okay, so while that's getting installed, what I want to show is, so since we're using our custom model and tokenizer, right? So there is some minor tweaks I had to do to the TRL library or the utilities that we need to make use of from that library. One is a slight tweak to their data collator class. So just have that copy tweaked here. And then the other things that we are going to make use of is just a simple routines that takes a data set and splits it into, in their formulation, they call it chosen and rejected. Then we are going to do this GC content based alignment. So I've just added those functions to compute those values. And a few other to convert the codon sequences into a form that the Gentlim's tokenizer would be compatible with. So let's see. Okay, great. So in terms of the requirements, all you need is the seed model or your SFT um, tuned model. In our case, it's the model supervised fine-tuned on the MDH family. You need the custom tokenizer for GenSlim, and then you need the sequences that are the bifurcated set of chosen and rejected. Okay, so I'll just quickly go through the training module. I think the others, the users can follow pretty easily. Very simply, so you have the sequence path, the tokenizer file, your reference model, that's your seed model you start with. You just give a directory for your output. And then the prepare dataset class basically gives you the train and eval data sets. And then you load your custom tokenizer with your tokenizer file. And then get data collator is nothing but a slight tweak to the DPO data collator that I mentioned, which is there in earlier cell. Then you're assigning the device. In this case, that will be a CUDA device. You're loading the model and the reference model, and then you're sending them to the devices. And you can, in a more, I think, command line setting, these are stuff that would be useful. You have your run directory set and so on and so forth. Okay, the two main blocks that are important is to declare the training args. So you have this DPO config imported from the TRL library. You give the output directory. And then I think I might have missed talking about, so an important parameter for the DPO is this quantity called beta. And that's there in the loss formulation. All it does is decides the weight at which you're preferentially weighing the preferred over the unpreferred sequences. So this value is a value roughly that varies from 0.1 to 0.01. So it's the order of that difference. You give your batch size, training epochs, grade accumulation steps, your learning rate. And then you can report to weights and biases if you need. And then comes the main module, which is the DPO trainer module. So you pass in your model that needs to be aligned, your reference model, supply the training logs, you supply your specific data collator, your train data set, your eval data set, your custom tokenizer. And then this max length in this case is pi12 because the MD8 sequences do not exceed that value in terms of the number of codons. And then this max prompt length is just I would say just a stupid mandatory requirement that the Deep Show trainer class needs. So you can just give a value of 128, or I think it can be even as small as 4. Okay, so once you instantiate with all of that, then you start the training. So let's do that. So this is all just encapsulated in this perform training function. Okay, so for this particular example, beta is 0.1. I've set a learning rate of 5 times 10 to the minus 5. 10 epochs. The chosen property I'm using for alignment is GC. And then the range over which I want to preferentially align is 45 to 55. And I'm choosing a batch size of 8. And this is my seed model, which is the supervised fine-tuned model on MDH. And let's just see. So hopefully it should work. All right, just outputs, just some numbers and sequences just to guide the user on what they expect from the run. Okay, in this particular case, you have chosen or the preferred sequences as 8,000 in count, and the non-preferred ones are about 24,000. So you have to discard the remaining around 16,000 sequences because you want the pairing of preferred and unpreferred. Okay, just like I said, it goes through, prepares the dataset object. And I think I'm also printing how a tokenized, a pre-tokenized version of the preferred and unpreferred sequences would look like. Okay, it looks like I need to sign in. So let's paste that here. And you can view your run at that URL. But yeah, so we gave a batch size of 8, right? So 7,000, roughly 7,000 samples divided by that number, you get 971 steps in this particular case for one epoch. So yeah, so the training progresses. So you'll see a bunch of metrics that will be outputted by the DQ trainer module. There'll be the rewards, the accuracies, and then the training loss. I think those are three most important ones. And then you should see something like what I showed as the loss going down, the rewards going up preferentially. So we can wait till one epoch gets completed, or we can actually stop here. Venkat, I'll leave it to you.
Yeah, no, this is great. I think yeah, I think the tutorials will be up on the summer school GitHub, so people can play with it. So no, this is amazing, Gautham. Thanks for
Thank you.
Amazing tutorial, and yeah, hopefully Alex can integrate the tutorials into the GitHub. So
awesome. Thank you
thanks,
so much,
Gautham.
Venkat. Yeah, really appreciate it. Yeah, thank you.
Yeah, thanks. Yeah, I'll follow up.